Okay, I'd like to start explaining why I think all the forces are the same force, changing its strength throughout the entire life of the universe. It might even be that the universe is always there the whole time, like a big loaf of space-time, like Einstein suggested, and that I'm just taking a slice through it now. Anyway, so I'm going to explain the C and B. So I'm taking this slice through it, let's say B equal to 0.9999833588271. So that's very close to the beginning of the universe, which when B would be equal to 1, the Big Bang. And I'm taking a radius of gamma 3.5757 times 10 to the 21, which is that one there. And why did I choose this value for B, for the C and B? Because it turns out that the age would then be correct, which is about 380,000 years, and more importantly, the redshift would be correct for the microwave background that we see now. It would have redshifted 1090, because remember back in the twin paradox I said that gamma plus phase velocity or whatever is the amount of redshift from 1. So that is the redshift, and instead of subtracting 1 I'm subtracting 2 pi. So I don't know, just makes it look better. But the main reason I'm choosing the C and B to have that B value is because just like the redshift, there's no requirement for a radius. You see, it's just a bare L and T, and the same applies to Dicky's equation. Once you simplify it, you find that you don't require a radius. So in other words, you can choose a B value without having to adjust it relative to the radius, which is sort of like a bit of a loop. So there's none of that. You just get this B value, which makes these values pop out. So you can see that is the inverse of the fine track structure constant, 137. You'll find that if I put in my mass calculation, that the C and the R cancel out, and the 4 goes underneath, and you put it across, and this and the mass goes upside down, and anyway it comes out to the same value. And so I have to prove that. So here's little g, I've called it a little g, and then capital G, which is the gravitational constant now, and if you take the ratio you find it's 137. And I will be using it to compare the strengths of the other 3 forces. You got A strong, A weak, A electromagnetic, which is the one we're doing now, and A gravity. That would be the mass of the C and B. Okay, and so why did I choose this B value for the universe now? So this is another slice through the block universe, maybe. 0.96297, etc., and a radius of gamma times 1.2 times 10 to the 26. Let's have a look. Well, find that the vacuum energy is about right. It should be 1.5 times 10 to the negative 9. It's a touch high, but joules per cubic meter. The age of the universe is spot on, 13.8 billion years old. That's a good value for the expansion rate. Hubble's value, 70, just about 71. 1 over time actually is the unit. And mass density there. Also, this is the universal acceleration that I've used to correctly calculate the rotation curves of galaxies. So that's another reason for choosing it. Cosmological redshifts basically gone. Permeability and cosmological constant. Okay, so what about charge? No, actually I'll just do one more calculation for another A value, a strong force. 2 times Planck length divided by the proton radius, and times the proton radius. What am I using? Capitals. Okay, so let's have a look. Just going to use this. Here we have the mass of the proton, and notice also that the gravitational force is shot right up to become the strong force, A little s. See that? That's the simplification of Dicke's equation. So little g over capital G. Alright. What about charge? Why is charge and Planck's constant, why are they constants? That's a good question. And the answer is this B value, H value, 1.74 times 10 to the negative 8. This is a constant of chemistry, basically. All the energy levels use it, and you don't find it in physics, but it seems to solve that problem. So put the radius of the first energy level, which is I'm calling O, and let's go n squared to get the different radiuses of the energy levels. Okay, now let's whiz down to the calculations. Pretty picture there. Now, according to the oil drop experiment of Minkowski and Mawson back in 100 years ago, the charge over any droplet is quantized, so the ratio is always the same. And notice that this is where H comes in, the H, and also the fine structure constant. You take the square of the fine structure constant and divide it by the square of my H value, and you get this ratio, this constant ratio of charge to mass for the electron. Okay, now when n is 1, you get the charges that many coulombs per electron, and Planck's constant, they don't have a unit for that, kilograms per meter squared over time, over seconds. And there's the energy level in EV. It's potential level energy. The potential has dropped from 0 to negative 13.6. This is the radius of that energy level. Oops, we don't need to worry about splitting because I don't think there is any. I don't know, probably is. Anyway, let's go to the second energy level, which is n equals 2. Notice that the charge hasn't changed, nor is the Planck's constant. They're remaining constant for some reason. I mean, I know what the reason is. It's because the B is constant, which is the H. I was talking about the H's. And it's the N, and the N cancels out. It only happens for this L cubed over T squared. It doesn't happen for any of the other values on the relativistic slide rule. So it just remains constant for all of chemistry, basically, all the energy levels. But everything else changes. So here's the second energy level. It's the potential energy is higher at negative 3.4 eV, and the radius is greater. It's really just n squared times that level of the n1 radius, and then you get the split, and this is correctly calculated here. 4.5 times 10 to the negative 5 eV is the total split, and you've got an up split and a down split, up split of 1/3 and down split of 2/3, and then you add them together and that's the total split. So that's correct for the fine structure, for hydrogen anyway. There's other fine structures which I haven't figured out. Okay, it should do it, I think. Yep. Oh, one more thing. It seems that if all the particles were created at this B value, when the gravity is the strong force, then to actually change the masses, all I have to do is change the radius. So if I change the radius, by the way, D is just that the ratio of the radius of the ratio of the mass of the proton to the mass of the electron, 1836. So now if I go and look for the mass somewhere down here, should be the where are you? Yeah, there it is. The mass of the electron, and it applies to all the quarks as well. You just adjust that proton radius to the radius of the actual particle, and you get the new mass. So that's a pretty simple way of changing masses. So gravity has got to the level of that strong force. So it's like this is right at the end of the universe, when everything is extremely uniform. You've just got this extremely strong gravitational force, and it would be very uniform because there's no particles before they all get created, and they have different radiuses. Yeah, I'm just jabbering on now. Anyway, that'll do, I think. Yep.